We're going to investigate the laws of logarithms today. These are the patterns that we can follow when we're trying to combine terms in logarithm form. They follow the laws of powers, or the laws of indices as you might have called them, because remember, a logarithm is a power. It is the power associated with a particular number, assuming a certain base. So let's start by reminding ourselves what the laws of indices are and seeing how we can adapt them to see them from the perspective of the powers themselves. Remember, 10 to the power of 3 multiplied by 10 to the power of 4 gives 10 to the power of 7. This is because when you multiply by 10 to the power of 4, you're multiplying by 10 4 times. Times 10 times 10 times 10 times 10. So 1,000 times 10,000 gives us 10 million. We can say the power of the product is the sum of the powers. In other words, the power of those two numbers multiplied, 10 cubed and 10 to the 4 multiplied together, the power of that, which is 7, is equal to the sum of what you get when you add the original powers. The powers of 10 cubed and 10 to the 4 are 3 and 4. Now let's look at the logarithms of those terms. So 10 cubed has a logarithm when we consider the base as 10. The logarithm will be 3. The power associated with 10 cubed is 3. The logarithm of 10 to the 4 is 4, and the logarithm base 10 of 10 to the 7 is 7. So when we look at the law that we've already seen enacted with indices, when we look at it from the perspective of the logarithms, what we're saying is, if you add the logarithms of the two numbers that are being multiplied, what you get is the logarithm of the result of multiplying those two numbers. Now what's interesting is, this doesn't just work for the examples we've looked at here. It's not just for nice numbers where the logarithms are pleasant and you can see exactly what's happening. If you take the log of 10 cubed and the log of 10 to the 4 and add those two separate logarithms, you do get the log of 10 cubed times 10 to the 4. But in general, this is always true. The logarithm of the product is the sum of the logarithms. If you compare those two statements, the only thing that's changed is the word power has been replaced with logarithm, because the logarithm is the power. This can be written more elegantly in this form. This is what we call the addition law. It's the law of logarithms from which all the other laws can be derived, and they all make sense in terms of this law. So we can say no matter what the two numbers are, if we can do log of each of them, adding those logs is the same as doing log of the product of the two numbers. Log base A of 15 and log base A of 20 added together will give you log base A of 15 times 20, 300. This will work in all sorts of situations. In fact, this is a good one to try for yourselves. If you calculate log base 10 of 500, and then compare it to the answers to log base 10 of 100 and log base 10 of 5, you should find that you can see the pattern emerging. It doesn't matter that the numbers are fairly nasty. Log base 10 of 100 is pretty nice, so that makes it easier to spot the pattern. I'd encourage you to pause and have a go at that. The next log law is subtracting. We're looking at what happens when you take things away. Now, just like before, we start by looking at division. The log law that determines what happens when you subtract logs comes from dividing terms. If you do 1,000,000 divided by 10,000, you get 100. And when we calculate that, looking at the powers, we're essentially doing 6 take away 4. That's where the 2 comes from. We could say here the power of the quotient is the difference of the powers. And therefore we can say the logarithm of the quotient is the difference of the logarithms. The easiest way to say this and to remember it is probably in the algebraic form. And if you look carefully, you'll see this kind of makes sense. If you add a logarithm, well, that's just like multiplying inside the logarithm. And so if you're subtracting logarithms, that translates to a division inside the logarithm. For the same reason that when you divide two numbers in index form, you subtract the indices. The logs are the powers. So when you're dividing two numbers and looking at the power that you get, that's equivalent to looking at the power that you would have got from each of the numbers separately and subtracting them. So this one's known as the subtraction law. And if you recall the numbers that you got on your calculator just now, log base 10 of 500 is about 2.7, and of course log base 10 of 100 is exactly 2, and it turns out log base 10 of 5 is about 0.7. So we could combine those three terms in different ways, and in one direction they give us evidence for the addition rule, but if we rearrange a little bit, we've got the subtraction rule. We know that log base 10 of 500 is equal to the sum of log base 10 of 100 and log base 10 of 5. But also, if we do log base 10 of 500 and then we subtract log base 10 of 100, we end up with log base 10 of 5. If you're curious, you can see how we can derive this algebraically. It looks a bit messy, but it's not as nasty as it seems. Remember, the rule works for any numbers. So in this case, instead of a and b, I'm going to put a over b and b into the addition rule. When we do that, you can combine them using the rule that we had before. The two separate logs added together can be turned into a single log with the two terms inside multiplied, and a over b multiplied by b is just a. So if log a over b plus log b is the same as log a, then that means log a over b must be the same as log a minus log b, and that's exactly the rule that we've got written at the top. The next law is to do with what happens when we multiply. Now, we're not talking about multiplying a log by a log. What we're talking about is multiplying a log by some number. And it's the equivalent to what happens when you have, say, 10 cubed to the power of 4 and you get an answer of 10 to the 12. But the nicest way, I think, to look at it is just as an extension of the addition rule. So look closely at this example. The addition rule tells us that log 100 plus log 100 is the same as log of 100 times 100. But then if you take that and then you add log 100, you'll be just turning it into log of 100 times 100 times 100. This rule can be applied repeatedly, and it can be applied with the same number over and over again if we want to, which means that we could simplify things a bit. In this case, we can see if we're assuming a log base 10, this would be 2 and 2 and 2 added together on the left-hand side. But on the right-hand side, the log of 100 times 100 times 100 is just going to be 6, because 100 times 100 times 100 is 1,000,000, so it has a logarithm of 6. Clearly, what's happening here is the number of terms we have on the left is determining how many 2's we end up with on the right. The simplest way of writing this expression is 3 lots of log 100 is equal to log of 100 cubed. And what's interesting here is you can change the base. That's why I've not included base 10 here. The line with the 2's and the 3 and the 6, that's assuming we have a base 10. But if you have a different base, those numbers change, but they are still valid. They're still equal. If you do 3 lots of log base 2 of 100, that'll be the same as log base 2 of 100 cubed. And in general, we can change that 3 into any other number, including non-whole numbers if we need to. So any number you like. We can think of this law as being a law that allows you to bring the power outside the logarithm. Log base a of something to the power of something is the same as the power being multiplied by log base a of the something. So this one's known as the power law. You can double check this for yourself. If you try 4 lots of log base 10 of 2, for instance, and then you have a go at log base 10 of 2 to the 4, which is log base 10 of 16, you'll find that those two things should come out exactly the same. It's worth being aware of a common mistake people make in this case. Log base 10 of 5 squared does fit the rule. It's something we can apply our rule to and say, well, log base 10 of 5 squared should be the same as 2 lots of log base 10 of 5. But log base 10 of 5 in a bracket squared is a very different thing. That just means log base 10 of 5 multiplied by log base 10 of 5. And that's not the same as 2 multiplied by log base 10 of 5. So be very careful. If in doubt, make sure you include brackets to demonstrate what's going on. I also want to show you just a couple more results. They don't quite qualify as laws because they're a little more restrictive or more specific, I suppose. They all come from laws of indices again. We'd start with this one. If you have any base whatsoever and you raise it to the power of 0, you always get an answer of 1. 3 to the 0 is 1, 17 to the 0 is 1, a half to the 0 is 1. And that means that if you take logs, with any base you like of the value 1, you get an answer of 0. We're saying the power associated with a value 1 is always 0. You haven't made anything bigger or smaller if you have a 1, so the number of times you've multiplied by your base is 0. Next, if you raise something to the power of 1, you get the same something you started with. 7 to the power of 1 is 7. 3.5 to the power of 1 is 3.5. So if you take logs with a base of a of the value a, you always get an answer of 1. The next one is worth pointing out, although it's not quite in the same category as the others. It's more like a non-result. It's a result you can never get. If you take a base, a normal positive number for your base, like 1.05 to represent a 5% increase, or 20 to represent multiplying by 20 every time, you raise it to the power of any number you like, no matter how big or small, positive or negative, you never get a negative answer. If you do 100 to the power of 0.5, you'll get 10. If you do 100 to the power of 0, you get 1. If you do 100 to the power of minus 2, you get 1 over 10,000. But you still don't get 0. You can get fractions, you can get numbers very, very small, but you can't ever get down to 0. And as a result, you can't find log base a of 0. It doesn't work. Try it on your calculator. Log base 10 of 0, log base 2 of 0. It doesn't work. There are no numbers that are sufficiently small that you can do log base anything of 0 and get that value. There's no sensible value that is attached to that. You can also, as a similar one related to this, you can never get negative values. If you try log base anything of a negative value, the calculator will tell you it's an error. Worth pointing out one additional thing, which is a bit more general and hopefully just a recap from when we first investigated logs, but this is a really important one to get your head around. The function log base a and a to the power of are called inverse functions. They are things which do the opposite of one another. Each one reverses the effect of the other one, just like squaring and square rooting, doubling and halving. They do the job of whatever the other function has done to change a number, this function will reverse that and get you right back to where you started. So if you do 10 to the power of 3.5, and then you give me your number, and I take your number and I do log base 10 of your number, I'll get back to 3.5. And if I give you a number like 1,000, and you do log base 10 of 1,000, well, you'll get 3. And then I do 10 to the power of your answer, 10 to the power of 3, well that just gets me back to 1,000. No matter what number you put in. If you apply these two functions, one after the other, they cancel out. It's as if nothing had ever happened. Now for a few examples. There's a few questions on here, I'm going to work through them one at a time. The first 3 are straightforward, the last one takes a bit more work. We're going to see how we can apply the laws of logarithms that we've talked about. So for the first one, we have 3 separate terms, and some are added and some are subtracted. The best way to deal with this is to apply the addition rule and the subtraction rule. Log base a of 6 plus log base a of 4 can be dealt with initially, right at the beginning. You can say those fit the rule that we've got. Log of capital A plus log of capital B gives log of capital A times capital B. So log of 6 plus log of 4 must be log of 24. And then you can say, well, we need to subtract log of 2. And when you subtract a log, it's equivalent to dividing inside the log. So here's the simplest way of writing it. Any log that's been added ends up contributing some factor to multiply by. And any log which is subtracted is the opposite, so you divide by it. It's worth noticing here, now we've talked about how you can bring a power down from inside a logarithm, well, minus log base a of 2 is equivalent to adding negative 1 times log base a of 2. And if you think of negative 1 as being a number in front of the log, that means it's a number that you could transfer inside the log. Call it add log base a of 2 to the negative 1. And 2 to the negative 1, as you can find out on your calculator if you are a bit rusty on this, 2 to the power of minus 1 is a half. So we can either think of this question as being a divide by 2 question or a multiply by a half question. Either way, we get the same answer. It's equivalent to log base a of 12. And in an exam, if you are asked to simplify this, it doesn't matter that it has a base of a, You could check at the end just by picking a number for the base to be. You could try log base 10 of 6 plus log base 10 of 4 minus log base 10 of 2 and check to see if you get the same answer as log base 10 of 12. And if you do, you've probably done it fine. For the second question, something a little bit different has happened. We no longer have terms that match the addition rule, although it might look like it initially. That's because it doesn't just say log 5 plus log 2. It has 2 lots of log 5 added to 3 lots of log 2. The best way to deal with this is to first use the power rule to bring the 2 and the 3 inside the logarithm. 2 lots of log 5 is the same as log of 5 squared, and 3 lots of log 2 is the same as log of 2 cubed. Once you've done that, you can safely apply the addition rule, because you have 2 logarithm terms which have no numbers in front, no coefficients, we say. So instead of having a 2 in front, we don't have anything in front of log base a of 5 squared. And instead of having a 3 in front, we don't have anything in front of log base a of 2 cubed. So we can apply the addition rule, which allows us to write a single logarithm with the 2 terms multiplied. And then we can multiply 5 squared and 2 cubed, and we should get 200. The next one looks scarier, but only because there are letters instead of numbers. The logic is still the same. We can bring the 2 inside the logarithm. So instead of writing 2 log x, we can write log of x squared. And then instead of n log y, we can write log of y to the n. I've left it with a minus outside because I think it makes life a bit easier for us, but there's no rule that says you have to. We could think of it as add log a of y to the minus n. And your final answer could equally well be log base a of x squared times y to the minus n. That means the same as x squared over y to the n. The last one, as I said, will take a bit more work. So we're going to do that over the next couple of slides. Before we start solving this, we're going to think about a scenario in which this equation would appear. So imagine I have 2 different investments. In one case, I've invested £200 and I'm getting a return of 10% interest every year. And in the other account, I've invested £300 and I get 5% interest every year. So I put less into the first account, but it's making more interest. It gets me 10% a year instead of 5%. The other account, however, I put more in at the beginning, so although it's not making as much interest, it already started ahead. Now the question might be, how long do I have to wait until the 10% interest account catches up with the 5% interest account? It should happen at some point, because if you're increasing by 10% instead of 5%, eventually you'll be increasing faster and faster, and you will overtake the one that's increasing more slowly. 1.1 is the percentage multiplier for a 10% increase, and 1.05 is the percentage multiplier for a 5% increase. Okay, let's see what happens when we try to apply log laws to this. We're going to start by simplifying a little bit first though. We'll divide both sides by 200. This is not essential. You can take logs straight away if you really want to, but this will make life a little bit easier for us. It saves us having 4 different terms at the end. We'll end up with 3. Still complicated, but possibly not quite as bad this way. If we can simplify a bit before we apply log laws, I usually do. Notice that 300 divided by 200 gives 1.5. You can do that on the calculator. We don't change the 1.05 to the n term because it's already been multiplied by the 300, and we're effectively multiplying it by 300 and dividing it by 200 all at once, which has the effect of multiplying by 1.5. Now, the term we want to find out is in the power. The term is actually a logarithm. N is some kind of logarithm. It's a power of 1.1, but also on the other side, a power of 1.05. And this is what makes it trickier than the other sort you might have already solved. If n appeared in one place, we'd do some simplifying, we'd take logs, and then we'd have n equals a number. But we need to do a bit more work with this one. Firstly, that doesn't make much sense to use a base of 1.1 or a base of 1.05, because no matter which one we use, we'll end up with something different on the other side of the equation. So I'm actually going to show you what happens if we take logs with a completely different base. But if you want to work through with a base of 1.1 or with a base of 1.05, as long as you stick with the same base, things will work just the same way. you might end up with something slightly simpler than what I've got. If we take logs, the first thing to write is exactly what you had written before, but with a big bracket around the whole thing, and then log base 10 or log base 1.1 or whatever you're using in front of it. This is important because it's very common for people to turn the right hand side into log of 1.5 multiplied by log of 1.05 to the n. But the log laws do not allow you to do that. There's no easy way to break apart or to apply logs separately to different pieces like that. We need to apply logs to the entire term on the right hand side and then see if there are any log rules that allow us to split them up. The next thing I'm going to do is start using our log rules. I'm interested in finding the value of n, and the way to do that is to bring it out of where it's hiding as a power, turn it into something which I can actually work with and manipulate. So I'm going to apply the power rule to the left hand side, bring that n outside. And then on the right hand side at the same time, I'm going to apply the addition rule that says if I've got the log of two things multiplied, it's equivalent to the log of each of the two separate things added together. And it looks like this. On the left, the n has come down in front, leaving me with log base 10 of 1.1. And on the right, the logarithm has been split into two separate logarithms. The reason this is important, although it may seem like it's made things more complicated, is that it allows me, for my next step, to do the same thing I did on the left to that term on the right hand side. Log base 10 of 1.05 to the n. I can bring the n down in front for my next line. Next. This is the line we got to, n log of 1.1 equals log of 1.5 plus log of 1.05 to the n. And the next thing I'm going to do, as I said, is apply the power rule to that final term on the right. Now, although it may not look like it, you are looking at a linear equation. 3x add 7 equals 4x minus 9. That's an example of a linear equation. It's one where the term you're interested in finding, in this case n, has only been multiplied by things and had stuff added on. There's nothing more complicated than that. Log base 10 of 1.1 is a messy number, and you could make it look messier by writing it as a decimal, for instance, but it's just a number for all that. There's nothing unknown about it. The n is the thing we don't know, and so I'm going to try to rearrange this so that n appears on its own on one side of the equation. To do that, I'm going to subtract n log 1.05 from both sides. And then factorize is a fancy way of saying notice that n is a factor of all of the terms on the left. So I can pull it out and call it n multiplied by log of 1.1 minus log of 1.05. That entire piece is now one big messy thing. This of course would have been easier if we'd had 5n minus 7n. You would say, well, 5 take away 7 is minus 2, so it's just minus 2n. That's essentially the same thing that we're doing, we just have messier numbers in front of n. But now we've got it looking like this. All we have to do is divide by the number of n's we have. If it said 17n equals 5, I'd divide by 17 and get n equals 5 over 17. Well, it doesn't say that, but these are just numbers, so I'm going to divide by that entire messy bracket on the left. And then plug it into a calculator, get a number. At the end, you should always check your value. Go back to the original equation and substitute 8.7 in and see what happens. In this case, you should get, I think, £458. It will take approximately 8.7 years before these two accounts have the same amount of money in them, and at that point they will both have £458 in them. The £200 account has been increasing by 10% for nearly 9 years, and the £300 account has been increasing by 5% for nearly 9 years, and at that moment, that's when they have the same amount of money. I want to point out briefly here, it's possible to write n slightly more simply than what I've got on that last line. We can use the subtraction law to combine the two terms in the denominator. In fact, you could have done it a line earlier when you first did n lots of something. I didn't think it was necessary because everything was something we could throw into the calculator, but it's worth noticing that it can be done. However, when you have a log divided by a log, there is no easy way to write that more simply. The law connecting logarithms and division is division of the terms inside the logarithm. Look back at the subtraction law and you'll see if you're subtracting two logs, you can simplify that to be the log of a quotient, the log of some kind of division process. But if you're dividing two logs, there's no easy way of dealing with that.